If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The Big Bang's legacy. Imagine a time when nothing existed, not even time itself. The universe, as we know it, was condensed into an unfathomably dense point, smaller than an atom, yet holding all the energy and matter that would form stars, galaxies, and everything we see today. Then, in a moment of unimaginable intensity, this singularity exploded. This cataclysmic event, known as the Big Bang, marked not only the birth of the universe but also the birth of space-time itself. It was the moment that set everything in motion, leading us to the question we're exploring today. Why does the universe expand? To understand the expansion, we must first grapple with the concept of the Big Bang as more than just an explosion. It wasn't matter being flung outward into a pre-existing space. It was space itself being created and expanding. This distinction is critical. The Big Bang was not an event in space. It was an event of space. During those first fractions of a second, the universe underwent a period of inflation. This wasn't a gentle swelling, but an exponential expansion, faster than the speed of light. In the span of less than a trillionth of a second, the universe grew from a subatomic scale to something measurable on a cosmic scale. This inflationary period laid the groundwork for the universe's continued expansion, setting the stage for the cosmic story that would unfold over billions of years. But what caused this initial inflation? Scientists believe it was driven by an enigmatic force that acted like a spring, stretching space-time outward. The energy of this expansion wasn't uniform, leaving tiny quantum fluctuations that would later become the seeds of galaxies. These imperfections in the fabric of space-time are one of the greatest clues we have to the universe's origin. As inflation slowed, the universe entered a hot, dense state filled with particles, radiation, and energy. This was the so-called hot Big Bang phase, a churning soup of quarks, electrons, and photons. Temperatures were so high that normal matter couldn't exist, and forces like gravity and electromagnetism were unified. Gradually, as the universe expanded, it cooled enough for quarks to combine into protons and neutrons, forming the nuclei of the first atoms. Yet, even in this chaotic infancy, expansion never ceased. It was as though the universe had been set on a path from which it could not deviate. This relentless expansion has remained a defining feature of the cosmos, shaping its evolution and structure. The legacy of the Big Bang is etched into the universe in profound ways. One of the most striking pieces of evidence is the cosmic microwave background radiation, CMB, a faint glow that permeates the cosmos. This radiation is a snapshot of the universe when it was just 380,000 years old, a time when it cooled enough for neutral atoms to form, allowing light to travel freely. The CMB reveals that the universe was remarkably uniform, but with slight variations, precisely the fluctuations left by inflation. The Big Bang's legacy is also evident in the composition of the universe. The abundance of light elements like hydrogen and helium matches predictions made by the theory. This primordial nucleosynthesis occurred within minutes of the Big Bang, providing further confirmation that this event is the universe's true beginning. But why did the Big Bang result in expansion rather than a static universe? The answer lies in the balance, or rather, the imbalance, of forces at play. The intense energy released during the Big Bang acted as a repulsive force, propelling space-time outward. Meanwhile, gravity worked as an opposing force, trying to pull everything back together. In those early moments, the universe's density was just right to allow expansion to continue without collapsing under gravity's weight. This balance has profound implications. If the universe had been slightly denser, it might have recollapsed into a big crunch. If it had been less dense, the rapid expansion could have ripped everything apart too quickly for stars and galaxies to form. Instead, we live in a universe where expansion proceeds at a pace that allows for cosmic evolution, a pace seemingly fine-tuned for life to exist billions of years later. The Big Bang's legacy isn't just written in the cosmos. It's embedded in every atom of your being. The carbon in your body, the oxygen you breathe, and the iron in your blood were forged in stars that formed because of this initial expansion. Without the Big Bang, there would be no stars, no planets, and no life. As we stand here today, Contemplating the cosmos, the universe's expansion continues. The question of why it expands and what keeps it going leads us to forces even more mysterious than the Big Bang itself. Dark energy, the force driving the acceleration of expansion, dominates the cosmos, but it remains one of the greatest enigmas of modern science. Yet it all began with the legacy of the Big Bang, a singular moment of creation that gave rise to everything. This chapter sets the stage for the story of the universe's expansion. As we delve deeper into topics like cosmic inflation, dark energy, and the ultimate fate of the universe, we'll uncover the forces and mysteries that drive this cosmic journey. Cosmic inflation. To grasp the universe's vastness and its ongoing expansion, we must journey back to a moment even earlier than the Big Bang's fiery aftermath, a time known as the era of cosmic inflation. This period, lasting mere fractions of a second, is one of the most mind-bending episodes in the history of the cosmos. During inflation, the universe expanded at a rate far surpassing the speed of light, growing exponentially and laying the foundation for the vast cosmic landscape we see today. But why did inflation occur? And what does it tell us about the universe's expansion? In the early moments of the Big Bang, the universe wasn't just a chaotic explosion of matter and energy. It was a seething, highly energetic quantum field governed by the laws of quantum mechanics. Within this primordial field, fluctuations in energy density caused pockets of spacetime to behave differently. One of these pockets underwent inflation, and that's the one that became our observable universe. The spark of inflation. The exact mechanism driving inflation remains a subject of intense scientific investigation. But one leading theory involves a hypothetical particle called the inflaton. The inflaton field, spread across the early universe, had a high-energy state that generated immense pressure. This pressure acted like an unstoppable spring, forcing spacetime to stretch at an exponential rate. Imagine blowing up a balloon, but instead of taking seconds or minutes, it inflates to astronomical scales in less than a trillionth of a second. During this rapid expansion, the distances between every point in the universe grew unimaginably large. To put it in perspective, if the universe were the size of a proton before inflation, it would have expanded to the size of a basketball almost instantly. This growth wasn't limited to matter or energy. It was space-time itself that was expanding, carrying everything along with it. The end of inflation and its aftermath. As the inflaton field's energy dissipated, inflation slowed and transitioned into what we recognize as the hot Big Bang phase. The energy released during this transition was converted into a dense soup of particles and radiation, setting the stage for the formation of matter, stars, and galaxies. This transition wasn't perfectly uniform, and that's a good thing. Tiny quantum fluctuations in the inflaton field left imprints on spacetime, creating regions of slightly higher or lower density. Over billions of years, these density variations would amplify under the influence of gravity, forming the cosmic web of galaxies and clusters we observe today. Evidence for inflation. Though inflation occurred at a scale and speed beyond direct observation, its fingerprints are visible across the cosmos. One of the most compelling pieces of evidence comes from the cosmic microwave background radiation, CMB. This faint afterglow of the Big Bang carries tiny variations in temperature, remnants of the quantum fluctuations seeded during inflation. Moreover, the uniformity of the CMB supports the idea that the universe underwent inflation. Without this rapid expansion, light from distant regions of the early universe wouldn't have had time to spread out evenly, leading to large-scale irregularities. Instead, we see remarkable homogeneity, interrupted only by the faint imprints of inflation's quantum origins. Another clue lies in the universe's geometry. Observations show that the cosmos appears flat, rather than curved, on large scales. Inflation explains this by stretching spacetime so extensively that any initial curvature was smoothed out, much like how the surface of a balloon appears flatter as it inflates. Inflation's role in ongoing expansion. While inflation ended billions of years ago, it set the stage for the universe's continued expansion. By creating a vast, nearly uniform spacetime, inflation ensured that the forces governing the universe could operate on large scales. It also established the conditions for the balance between gravity and expansion, preventing the cosmos from collapsing or ripping apart prematurely. Interestingly, inflation might also explain why the universe's expansion is accelerating today. Some theories suggest that dark energy, the mysterious force driving this acceleration, is related to the same energy that powered inflation. If true, the inflaton field may have left behind a residual force that, while much weaker than during inflation, continues to influence spacetime. Theoretical challenges and open questions. Despite its success in explaining many cosmic phenomena, inflation raises profound questions. For one, what caused the inflaton field to exist, and why did it behave the way it did? Additionally, why did inflation end in some regions while potentially continuing in others? Some models suggest that inflation is still happening in distant parts of the cosmos, creating a multiverse of universes, each with its own physical laws and properties. Another challenge involves reconciling inflation with quantum mechanics. If quantum fluctuations seeded the structure of the universe, how do they align with general relativity, which governs spacetime on large scales? This tension between the quantum and the cosmic remains one of the great puzzles of modern physics. Inflation and the multiverse. One of the most fascinating implications of inflation is the possibility of a multiverse. If inflation happened in different regions of spacetime at different rates, it could have created bubbles of reality, each forming its own universe with unique characteristics. Our universe would simply be one bubble among an infinite cosmic sea. This idea, while speculative, opens profound questions about the nature of reality and whether our universe's expansion is just one chapter in a much larger story. The legacy of inflation. Cosmic inflation was the universe's most dramatic growth spurt, a fleeting but transformative moment that set everything in motion. Without it, the cosmos might be unrecognizably different, or might not exist at all. It explains why the universe expands, why it's structured the way it is, and why it appears so uniform on large scales. Yet inflation isn't just a relic of the past. It's a reminder that the universe operates on scales and principles far beyond human comprehension. It invites us to explore deeper questions about where we came from, where we're going, and what lies beyond the observable universe. As we move forward in our journey through the cosmos, we'll encounter even more mysteries, from the role of energy in driving expansion to the enigmatic force of dark energy itself. Each step brings us closer to understanding the ultimate question: why does the universe expand? The role of energy. To understand why the universe expands, we must delve into the heart of its mechanics. Energy. In the cosmic theater, energy is both the conductor and the orchestra, orchestrating the universe's expansion, evolution, and eventual fate. From the fiery birth of the cosmos to its current accelerating growth, energy has always been the invisible hand guiding the motion of spacetime. But what is energy in the context of the universe? And how does it drive the cosmos to expand rather than collapse or remain static? Energy as the engine of expansion. Energy, in its various forms, is the foundation of the universe. It exists not only in matter, radiation, and particles, but also in spacetime itself. During the Big Bang, an incomprehensible amount of energy was released, setting the universe in motion. This wasn't energy in the sense of fire or heat. It was a primal force embedded in spacetime, giving birth to all the matter and forces we know. One of the most critical aspects of this energy is its relationship to spacetime. In Einstein's theory of general relativity, energy and matter dictate the curvature of spacetime. In turn, this curvature determines how objects move and how spacetime itself evolves. In the early universe, the energy density was so high that it stretched spacetime outward, creating the phenomenon we now call expansion. Kinetic energy and expansion. In the universe's infancy, kinetic energy played a pivotal role. This energy, associated with motion, was a product of the intense velocities at which particles moved in the hot, dense environment. These particles, driven by the immense energy of the Big Bang, pushed outward, contributing to the expansion of the universe. However, this motion wasn't like a cannonball being shot into space. The kinetic energy of the early universe wasn't just about particles moving. It was spacetime itself, expanding, dragging everything along with it. This distinction is key. In an expanding universe, kinetic energy isn't just about matter. It's also about the stretching of space-time. Potential energy in space-time. Another critical player in cosmic expansion is potential energy, particularly in the form of vacuum energy. This energy is an inherent property of space itself, even in the absence of matter or radiation. During the inflationary period, the potential energy of the inflaton field acted like a spring, fueling the exponential growth of the universe. This idea is deeply tied to the concept of vacuum energy, which persists even in the empty regions of space. Far from being a void, the vacuum of space is alive with quantum fluctuations and latent energy. This energy contributes to the universe's expansion by creating a pressure that counteracts gravity, allowing space-time to stretch. Radiation's early dominance. In the first few 100,000 years after the Big Bang, radiation was the dominant form of energy in the universe. This radiation, in the form of photons and other high-energy particles, exerted a pressure that influenced the rate of expansion. The energy density of radiation was incredibly high, meaning it contributed significantly to the universe's overall energy budget. However, as the universe expanded, radiation became less dominant. This is because radiation's energy density decreases more rapidly than that of matter as space-time stretches. The reason lies in the nature of radiation. As the universe expands, the wavelength of light stretches, reducing its energy, a phenomenon known as redshift. This gradual loss of energy shifted the cosmic balance, allowing matter to take the lead. The transition to matter dominance. As the universe cooled, matter began to clump together, forming the first atoms, stars, and galaxies. The energy stored in matter, primarily in the form of mass energy, became the dominant factor in shaping the cosmos. According to Einstein's famous equation, E equals mc2, E equals mc caret 2, E equals mc2, matter itself is a form of energy, and its gravitational influence dictated the structure and behavior of the universe for billions of years. Matter's dominance marked a slower phase of expansion. Gravity, acting as a counterforce, worked to pull matter together, creating the cosmic structures we see today. Yet, this gravitational pull was never strong enough to halt expansion entirely, thanks to the initial energy imparted during the Big Bang. The emergence of dark energy. Approximately 5 billion years ago, the universe's energy dynamics took a dramatic turn. Observations revealed that the expansion of the universe wasn't slowing down, as scientists had expected. It was accelerating. This acceleration pointed to a mysterious form of energy that came to dominate the cosmos: dark energy. Dark energy is unlike anything else we know. It's not tied to matter or radiation, but exists as an intrinsic property of space-time. Its nature remains one of the greatest mysteries in physics, but its effects are undeniable. Dark energy acts as a repulsive force, counteracting gravity and driving the universe's expansion at an ever-increasing pace. One theory suggests that dark energy is related to the vacuum energy of space-time. As the universe expands, the vacuum energy remains constant, meaning its influence grows as the volume of space increases. This phenomenon explains why dark energy became dominant only in the later stages of the universe's history. The interplay of energy forms. The story of the universe's expansion is, in essence, a story of changing energy dynamics. In the early universe, radiation reigned supreme, its energy driving rapid expansion. As the universe aged, matter took over, slowing expansion and allowing galaxies and stars to form. Finally, dark energy emerged as the dominant force, accelerating the cosmos into an unknown future. This interplay highlights a profound truth. The universe is a dynamic system, constantly evolving as the balance of energy shifts. Each phase, radiation-dominated, matter-dominated, and dark energy-dominated, marks a new chapter in the cosmos' story, each with its own implications for expansion. Energy conservation in an expanding universe. One of the most intriguing aspects of energy in the universe is how it behaves during expansion. In everyday life, energy is conserved. It can't be created or destroyed, only transformed. But in the context of an expanding universe, energy conservation takes on a new meaning. As space-time stretches, the energy of radiation decreases due to redshift. Yet this energy doesn't simply disappear. It's absorbed into the fabric of space-time itself. Similarly, the vacuum energy of dark energy remains constant even as the universe expands, suggesting that the rules governing energy conservation are more complex on cosmic scales. The role of energy in the universe is fate. The ultimate fate of the universe hinges on its energy composition. If dark energy continues to dominate, the cosmos will expand forever, leading to a big freeze where galaxies drift apart and stars burn out. Alternatively, if dark energy's properties change, it could lead to scenarios like the Big Rip or even a reversal of expansion into a big crunch. These possibilities depend on the interplay of energy forms in the universe. Understanding this balance is critical to unraveling the mystery of why the universe expands and what lies ahead. A universe defined by energy. From the explosive energy of the Big Bang to the enigmatic force of dark energy, the universe's expansion is inextricably tied to its energy dynamics. Energy isn't just a byproduct of cosmic events, it's the driving force behind them, shaping the cosmos at every scale. Space-time itself expanding. When we talk about the expansion of the universe, it's natural to imagine galaxies zooming through space like cars on a highway. However, this mental picture is misleading. The universe's expansion is not about galaxies moving through a pre-existing void. It is the expansion of space-time itself. This distinction is profound and underpins our understanding of why the universe expands and how it behaves on cosmic scales. But what does it mean for space-time to expand? How can something as abstract as the fabric of the cosmos stretch? And what implications does this have for the universe we observe today? The nature of space-time. Space-time, as described by Einstein's theory of general relativity, is the four-dimensional fabric of the universe, combining the three dimensions of space with time as the fourth. In this model, space-time isn't a passive backdrop. It's dynamic, capable of bending, stretching, and warping in response to the presence of energy and mass. When we say that space-time is expanding, we mean that the very metric defining the distances between points in the universe is increasing. This isn't akin to objects moving within space, but rather space itself growing, carrying everything within it along for the ride. The metric of expansion. The expansion of space-time is mathematically described by the Friedman, Lemaitre, Robertson, Walker, FLRW, metric, which governs how distances change in an expanding universe. The key concept here is the scale factor, a dimensionless number that increases as the universe expands. Over time, the scale factor grows, meaning that the distances between galaxies grow proportionally. Importantly, this expansion doesn't affect structures bound by gravity, like galaxies or solar systems. The gravitational forces within these systems are strong enough to resist the stretching of space-time. Thus, while galaxies move farther apart on large scales, the internal dynamics of stars, planets, and atoms remain unchanged. The evidence for expanding space-time. The most direct evidence for space-time expansion comes from the phenomenon of cosmic redshift. When light travels through an expanding universe, its wavelength stretches, shifting toward the red end of the spectrum. This redshift isn't due to the motion of galaxies through space, but to the stretching of space-time itself. The light's wavelength elongates as space-time expands, providing a cosmic record of the universe's growth. Another compelling piece of evidence is the cosmic microwave background radiation (CMB). This faint afterglow of the Big Bang shows the universe as it was approximately 380,000 years after its birth. The CMB's uniformity and tiny fluctuations reveal the imprint of an expanding space-time that has stretched over billions of years. The expanding universe, of a balloon analogy. To visualize space-time's expansion, consider the analogy of a balloon being inflated. Imagine that galaxies are dots drawn on the balloon's surface. As the balloon expands, the dots move farther apart, not because they are moving on the surface, but because the surface itself is stretching. This analogy captures the essence of an expanding universe, though it's important to note that the universe has no edge or center like a balloon. The balloon analogy also highlights an important feature. Every point on the surface appears to be the center of expansion. This is true for the universe as well. From any galaxy's perspective, all other galaxies appear to be moving away, giving the illusion that the observer's galaxy is at the center of the cosmos. What drives the expansion? The expansion of space-time is driven by the energy content of the universe. During the Big Bang, the initial energy density set the universe in motion, creating an outward push. Over time, the nature of this energy has evolved. In the early universe, radiation dominated, followed by matter. Today, dark energy, an enigmatic force, is the primary driver of expansion, causing the rate of growth to accelerate. Dark energy's role in the expansion of space-time is particularly intriguing. It exerts a negative pressure, effectively acting as a repulsive force that stretches space-time at an increasing pace. This acceleration is measured by observing distant supernovae and mapping the large-scale structure of the cosmos. Does space-time have limits? One of the most profound questions about expanding space-time is whether it has limits. The observable universe, defined by the farthest light we can see, is about 93 billion light-years across. However, this is only the portion of space-time we can observe. The total universe could be far larger, or even infinite. If the universe is infinite, its expansion doesn't create more space, but increases the distances between points. If it's finite, the expansion could continue indefinitely, stretching space-time into an ever larger, but still bounded volume. Local structures versus cosmic expansion. While space-time expands on large scales, local structures like galaxies, stars, and planets are unaffected. This is because gravity dominates at smaller scales, binding objects together and preventing space-time's expansion from pulling them apart. For example, the Milky Way and the Andromeda Galaxy are on a collision course despite the overall expansion of the universe. Their mutual gravitational attraction outweighs the effects of expanding space-time on this scale. Similarly, within our solar system, the gravitational pull of the Sun ensures that the planets remain in stable orbits. The observable effects of expanding space-time. Expanding space-time influences everything we observe in the cosmos. It shapes the large-scale structure of the universe, creating vast voids between clusters of galaxies. It also affects time, as the stretching of space-time alters how we measure distances and durations on cosmic scales. This expansion also means that the universe looks different at different times. The farther we look into space, the further back in time we see, revealing a younger, denser, and hotter universe. This ability to peer into the past is one of the most remarkable aspects of an expanding space-time. The role of space-time in cosmic fate. The future of the universe depends on how space-time continues to expand. If dark energy remains constant, the universe will expand forever, leading to a big freeze where stars burn out and galaxies drift apart. Alternatively, if dark energy grows stronger, it could lead to a big rip, tearing apart galaxies, stars, and even atoms. These scenarios are governed by the dynamics of space-time and the forces acting upon it. Understanding these forces is key to unraveling the ultimate fate of the cosmos. Why does space-time expand? The expansion of space-time isn't just a physical process. It's a reflection of the universe's underlying laws. Einstein's equations of general relativity show that space-time is shaped by energy and mass, and the universe's initial conditions set it on a path of perpetual expansion. This expansion is a natural outcome of the interplay between energy, gravity, and the geometry of space-time. In many ways, the expansion of space-time is the universe's most fundamental feature. It defines the cosmos not as a static entity, but as a dynamic, evolving system, forever growing and changing. Hubble's law. The discovery of the universe's expansion was one of the most transformative moments in human history, reshaping our understanding of the cosmos and our place within it. At the heart of this revelation is Hubble's law, a cornerstone of modern cosmology that provides the observational foundation for the concept of an expanding universe. But what is Hubble's law, and how did it revolutionize our view of the cosmos? To understand its significance, we must step into the early 20th century, when astronomers were grappling with the nature of the universe, the era before Hubble. At the start of the 20th century, The prevailing view of the universe was vastly different from what we know today. Most scientists believed in a static, eternal universe where stars and galaxies were fixed in place. The concept of an expanding universe was not even on the radar, and the Milky Way was thought to encompass the entirety of the cosmos. This view began to shift with advances in telescope technology. In the 1920s, astronomer Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to study distant objects called spiral nebulae. At the time, there was intense debate about whether these nebulae were part of the Milky Way or distant island universes of their own. Hubble's observations settled the debate. By identifying Cepheid variable stars in these nebulae, he calculated their distances and found that they lay far beyond the Milky Way. These nebulae were, in fact, other galaxies, revealing that the universe was far larger than previously imagined. Hubble's breakthrough discovery. Hubble's work didn't stop at proving the existence of other galaxies. As he measured their distances, he also studied their light spectra, which carried a surprising clue. The light from these galaxies appeared to be redshifted, meaning their wavelengths were stretched toward the red end of the spectrum. This redshift indicated that the galaxies were moving away from us. What's more, Hubble noticed a pattern. The farther a galaxy was, the greater its redshift, and thus, the faster it was receding. This relationship between a galaxy's distance and its velocity became known as Hubble's law, expressed mathematically as V equals h0 dv equals h_0 backslash dot dv equals h0d. Here, VVV is the galaxy's recessional velocity. h0 h_0 is the Hubble constant, representing the rate of expansion. DDD is the galaxy's distance from us. This simple, yet profound equation encapsulates the essence of an expanding universe. The farther away a galaxy is, the faster it moves away. Hubble's discovery provided the first direct evidence that the universe is not static but dynamic, expanding like the surface of an inflating balloon. The significance of redshift. The redshift of light from distant galaxies is a key piece of evidence for the universe's expansion. But what causes this redshift? It's not the result of galaxies moving through space. Instead, it's due to the stretching of spacetime itself. As the universe expands, the wavelengths of light traveling through it are stretched, increasing their wavelength and shifting them toward the red end of the spectrum. This phenomenon, called cosmological redshift, is distinct from the Doppler effect, which occurs when an object moves through a medium like air or water. Cosmological redshift is a direct consequence of the expansion of spacetime, providing a cosmic fingerprint of the universe's growth. Measuring the Hubble constant. The Hubble constant, h0 h_0 is a critical value in cosmology, representing the rate of the universe's expansion. Determining this value has been a central goal for astronomers, but it has proven surprisingly difficult. Hubble's original estimate of h0 h_0 was much higher than today's accepted range, largely due to inaccuracies in measuring distances. Modern observations, using tools like the Hubble Space Telescope and surveys of Type Ia supernovae, have refined the value of h0 h_0 to around 70 kilometers per second per megaparsec. This means that for every megaparsec, approximately 3.26 million light-years of distance, a galaxy's recessional velocity increases by about 70 kilometers per second. However, there remains a significant tension between different methods of measuring h0 h_0. Observations of the cosmic microwave background, CMB, suggest a slightly lower value, while measurements based on nearby supernovae yield a higher value. This discrepancy, known as the Hubble tension, is one of the most intriguing puzzles in cosmology today. Implications of Hubble's law. Hubble's law has profound implications for our understanding of the universe. First and foremost, it confirms that the universe is expanding. This expansion is not a motion through space, but an expansion of space itself, carrying galaxies along with it. Hubble's discovery also provided critical evidence for the Big Bang theory. If the universe is expanding, it must have been smaller in the past. By extrapolating backward, we can trace the expansion to a singular point of origin approximately 13.8 billion years ago, the moment of the Big Bang. Moreover, Hubble's law reveals that there is no center to the universe's expansion. From any point in the cosmos, it appears as though all other galaxies are moving away. This observation aligns with the cosmological principle, which states that the universe is homogeneous and isotropic on large scales, with no preferred location or direction. Beyond the observable universe, Hubble's law also implies that there are regions of the universe we cannot see. As galaxies recede at ever-increasing velocities, some are moving away faster than the speed of light due to the expansion of spacetime. These galaxies have crossed the cosmic horizon, meaning their light can no longer reach us. This creates a limit to the observable universe, currently about 93 billion light-years in diameter, even though the actual universe may be much larger, or infinite. Challenges and refinements. While Hubble's law is a cornerstone of cosmology, it's not without challenges. For one, the relationship between distance and velocity becomes more complex at extreme distances, where dark energy's influence causes the rate of expansion to accelerate. Additionally, local gravitational effects can create deviations from Hubble's law. For instance, nearby galaxies like Andromeda are not receding from us, but are instead on a collision course due to gravitational attraction. These local dynamics must be accounted for when studying the broader pattern of cosmic expansion. Hubble's legacy. The discovery of Hubble's law marked a turning point in our understanding of the universe. It shattered the notion of a static cosmos and opened the door to a dynamic, evolving universe governed by the interplay of energy, gravity, and spacetime. Hubble's work also inspired generations of scientists to explore the mysteries of cosmic expansion. It laid the groundwork for theories of dark energy, inflation, and the ultimate fate of the universe, all of which are rooted in the fundamental idea that spacetime itself is expanding. Redshift as evidence. One of the most compelling pieces of evidence for the universe's expansion lies in a phenomenon known as redshift. This observable shift in the wavelength of light from distant galaxies provides a direct window into the stretching of spacetime itself. Redshift is not merely an abstract concept. It is a cosmic signpost, written in the light of stars, that reveals the dynamic nature of our universe. But what exactly is redshift? How does it occur? And why is it so central to our understanding of cosmic expansion? Let's unravel the story of redshift and its profound implications. The nature of light and wavelengths. To understand redshift, we must first grasp the nature of light. Light travels as waves, with its color determined by the wavelength. Shorter wavelengths correspond to blue or violet light, while longer wavelengths correspond to red light. When light interacts with objects in motion, its wavelength can change, a phenomenon known as the Doppler effect. The Doppler effect is familiar in everyday life. Imagine standing by a road as a car drives past, its engine's pitch rising as it approaches and dropping as it recedes. This change in pitch occurs because the sound waves are compressed when the car moves toward you, shorter wavelength, and stretched when it moves away, longer wavelength. A similar effect occurs with light, but in the cosmic context, the stretching of light waves is not due to motion through space. Instead, it's caused by the expansion of spacetime itself. Cosmological redshift, a signature of expansion. When we observe light from distant galaxies, we find that it is shifted toward longer wavelengths, appearing redder than it should. This is known as cosmological redshift, and it is fundamentally different from the Doppler shift caused by objects moving through a medium. In an expanding universe, spacetime itself is stretching. As light travels through this stretching spacetime, its wavelength is elongated. This process increases the wavelength of the light, shifting it toward the red end of the spectrum. Importantly, this redshift occurs not because the galaxies are moving through space, but because the very fabric of space is expanding. Measuring redshift. Astronomers quantify redshift using a parameter called ZZZ, defined as Z equals observed minus emitted equals \frac lambda underscore text observed lambda underscore text emitted lambda underscore text emitted Z equals emitted observed minus emitted. Here, observed lambda underscore text observed is the wavelength of the light as we observe it. Emitted lambda underscore text emitted Emitted is the wavelength of the light when it was emitted by the source. A higher ZZZ value indicates a greater redshift, which corresponds to a more distant galaxy. This relationship allows astronomers to use redshift as a tool to measure distances and trace the expansion history of the universe. The link between redshift and distance. Hubble's law, discussed in the previous chapter, establishes a direct relationship between redshift and distance. The farther away a galaxy is, the greater its redshift, and the faster it is receding from us. This correlation is a cornerstone of cosmology, enabling astronomers to map the universe's large-scale structure and determine its rate of expansion. For nearby galaxies, redshift provides a straightforward measure of velocity. For more distant galaxies, where space-time stretching becomes more significant, redshift reflects the cumulative effect of expansion over billions of years. The role of spectroscopy. The discovery of redshift relies on a powerful technique called spectroscopy, which analyzes the light from celestial objects. By breaking light into its component colors, astronomers can study its spectrum, identifying characteristic patterns of absorption or emission lines created by specific elements. For example, hydrogen emits light at precise wavelengths, producing a signature pattern in the spectrum. If this pattern is shifted toward longer wavelengths, astronomers can calculate the galaxy's redshift. The consistency of these spectral fingerprints across vast distances allows for highly accurate measurements. Redshift and the cosmic microwave background. Cosmological redshift isn't limited to visible light. It affects all forms of electromagnetic radiation. One of the most profound examples is the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. Initially emitted as high-energy gamma rays, the CMB's wavelengths have been stretched by the expansion of space-time to the microwave region of the spectrum. The CMB's redshift provides a direct measurement of how much the universe has expanded since its earliest moments, offering invaluable insights into its age, composition, and dynamics. The expanding universe through redshift. Redshift is more than just evidence of the universe's expansion. It's a tool for exploring its history. By observing galaxies at different redshifts, astronomers effectively look back in time, witnessing the universe at various stages of its evolution. For example, galaxies with low redshift, Z is almost equal to 0.01 Z / approximate 0.01 Z is almost equal to 0.01, are relatively nearby and reflect the universe as it is today. Galaxies with moderate redshift, Z is almost equal to 1 Z / approximate 1 Z is almost equal to 1, reveal the universe as it was billions of years ago when star formation peaked. Galaxies with high redshift, Z greater than 6 Z greater than 6 Z greater than 6, show the cosmos in its infancy, during the epoch of reionization when the first stars and galaxies were forming. The Hubble tension, redshift's role and controversy. Redshift measurements are central to one of modern cosmology's biggest debates, the Hubble tension. Observations of nearby galaxies and supernovae yield a higher value for the Hubble constant, H0, H_0 H0, than measurements based on the CMB and early universe data. This discrepancy raises questions about whether our understanding of redshift, expansion, or dark energy needs revision. Some theories propose that the tension reflects new physics, such as variations in dark energy or interactions between dark matter and radiation. Others suggest it may stem from systematic errors in measurements. Either way, redshift remains at the heart of this cosmic puzzle. Redshift beyond the observable universe. As the universe expands, there are regions where redshift becomes extreme. Galaxies beyond a certain distance recede from us faster than the speed of light due to the expansion of space-time. Their light can no longer reach us, placing them beyond the cosmic horizon. This phenomenon limits our observable universe, but also underscores the vastness of the cosmos. Challenges and mysteries of redshift. While redshift is a powerful tool, it is not without challenges. For instance, gravitational effects can distort redshift, particularly in regions with massive structures like galaxy clusters. Intergalactic dust can alter the observed spectrum, complicating redshift measurements. Despite these challenges, redshift remains one of the most robust methods for studying cosmic expansion. The legacy of redshift. The discovery of redshift was a watershed moment in astronomy. revealing that the universe is not static but expanding. It transformed light into a cosmic time machine, allowing us to trace the universe's growth and evolution across billions of years. Dark energy's mystery. If the universe's expansion is a story, then dark energy is its most enigmatic character. This mysterious force, accounting for roughly 68% of the universe's energy content, is responsible for the accelerating expansion of space-time. Its nature, origin, and implications remain one of the greatest puzzles in modern cosmology. But what is dark energy? How do we know it exists? And why does it play such a dominant role in the cosmos? Let's embark on a journey into the heart of this cosmic mystery. The discovery of dark energy. The story of dark energy begins in the late 20th century, when astronomers set out to measure the universe's expansion rate. They expected to find that expansion was slowing due to the gravitational pull of matter. Instead, their observations revealed something extraordinary. The expansion of the universe is not decelerating, it's accelerating. This groundbreaking discovery came from studies of type Ia supernovae, which are excellent standard candles for measuring cosmic distances. These exploding stars shine with a predictable brightness, allowing astronomers to calculate their distance and compare it to their redshift. The results showed that distant supernovae were dimmer than expected, indicating that they were farther away than predicted by a decelerating universe. This unexpected acceleration required a new explanation, and dark energy was introduced as the mysterious force driving this phenomenon. The nature of dark energy. Dark energy is unlike anything else in the universe. It is not matter, nor is it radiation. Instead, it appears to be a property of space-time itself, exerting a negative pressure that counteracts gravity and drives expansion. One leading explanation is that dark energy is tied to the cosmological constant, a term introduced by Einstein in his equations of general relativity. The cosmological constant represents a uniform energy density inherent to space-time, which remains constant as the universe expands. Though Einstein originally abandoned the idea, calling it his greatest blunder, it was revived to explain the accelerating expansion. Another possibility is that dark energy is a dynamic field, sometimes referred to as quintessence, which evolves over time. Unlike the cosmological constant, quintessence can vary in strength and influence, potentially changing the rate of expansion. Evidence for dark energy. The evidence for dark energy is compelling and comes from multiple independent sources. 1. Supernova observations. Type Ia supernovae studies directly show that the universe's expansion is accelerating. This remains the most direct evidence for dark energy. 2. Cosmic microwave background, CMB. Observations of the CMB reveal the early universe's geometry and energy composition. The data show that the universe is flat and that dark energy is needed to account for its current state. 3. Large-scale structure. The distribution of galaxies and cosmic voids reflects the influence of dark energy. Its repulsive force affects how structures form and evolve over time. 4. Baryon acoustic oscillations, BAOs. These are subtle ripples in the distribution of galaxies, remnants of sound waves from the early universe. Their patterns confirm the presence of dark energy. Dark energy's role in cosmic expansion. Dark energy dominates the universe's energy budget, dwarfing both matter, 27%, and radiation, less than 1%. Its influence grows as the universe expands, because its energy density remains constant while the density of matter and radiation decreases. This dominance explains why the universe's expansion shifted from decelerating to accelerating approximately 5 billion years ago. Before this era, matter's gravitational pull was strong enough to slow expansion. As the universe expanded, matter became less dense, allowing dark energy's repulsive force to take over. Theories of dark energy. Several theories attempt to explain the nature of dark energy. 1. Cosmological constant. The simplest explanation, the cosmological constant, lambda/lambda, posits that dark energy is an intrinsic property of space-time. It represents a constant energy density that remains unchanged over time. 2. Quintessence. This dynamic field theory suggests that dark energy evolves, with its strength and influence varying throughout cosmic history. If true, quintessence could lead to different fates for the universe, depending on its behavior. 3. Modified gravity. Some theories propose that dark energy isn't a separate force, but a manifestation of modifications to general relativity. These models suggest that gravity behaves differently on cosmic scales, producing the effects attributed to dark energy. 4. Extra dimensions. String theory and related frameworks propose that dark energy might arise from interactions in higher dimensions, influencing the expansion of our 3D universe. 5. Emergent phenomena. Some speculative ideas suggest that dark energy is an emergent property of the universe, arising from quantum mechanics, entropy, or other fundamental processes. The challenges of studying dark energy. Dark energy is extraordinarily difficult to study because it doesn't interact with matter or light. Its presence is inferred entirely from its effects on spacetime and cosmic structures. This elusiveness makes it one of the most mysterious components of the universe. To uncover its secrets, scientists rely on indirect methods, such as mapping the expansion rate through supernovae and galaxy surveys, studying the CMB for imprints of dark energy's influence, using gravitational lensing to trace its effects on the curvature of spacetime. Upcoming observatories like the James Webb Space Telescope, JWST, and the Euclid mission aim to provide deeper insights into dark energy by observing distant galaxies and cosmic phenomena with unprecedented precision. The ultimate fate of the universe. Dark energy holds the key to the universe's ultimate fate. Its influence will determine whether the cosmos continues to expand forever or meets a more dramatic end. Several scenarios arise depending on dark energy's nature. 1. Big freeze. If dark energy remains constant, the universe will expand forever, cooling as galaxies drift apart. Stars will burn out, leaving a dark, frozen cosmos. 2. Big rip. If dark energy's strength increases over time, it could tear apart galaxies, stars, and even atoms in a cataclysmic big rip. 3. Cosmic rebound. If dark energy changes sign or reverses, it could lead to a contraction phase, culminating in a big crunch. 4. New physics. If dark energy is dynamic, it might transition into an unknown state, triggering phenomena beyond our current understanding. The legacy of dark energy. Dark energy is a reminder of the universe's boundless mysteries. Despite its invisibility, it shapes the cosmos on the largest scales, influencing everything from galaxy formation to the flow of time itself. Its discovery has revolutionized cosmology, challenging us to rethink the fundamental forces that govern existence. As we continue to explore, dark energy beckons us toward the edges of knowledge, inspiring new questions about the nature of reality and our place in the grand cosmic story. Cosmological constant. The cosmological constant, denoted by the Greek letter lambda/lambda, is a concept with a history as enigmatic as the force it represents. Introduced by Albert Einstein in 1917, lambda/lambda began as a mathematical addition to his equations of general relativity, only to be dismissed and later resurrected as a cornerstone of modern cosmology. Today, it is central to our understanding of dark energy and the accelerating expansion of the universe. But what exactly is the cosmological constant? Why was it introduced, abandoned, and revived? Let's explore this fascinating concept and its profound implications for the fate of the cosmos. The birth of the cosmological constant. When Einstein formulated his theory of general relativity, he revolutionized our understanding of gravity. Instead of viewing gravity as a force between masses, he described it as the curvature of spacetime caused by mass and energy. His equations predicted a dynamic universe, one that either expanded or contracted under the influence of gravity. However, this prediction clashed with the scientific consensus of the time. The prevailing belief was that the universe was static and eternal, with stars and galaxies fixed in place. To align his theory with this idea, Einstein introduced the cosmological constant, lambda/lambda, a term that acted as a repulsive force, countering gravity and allowing the universe to remain stable and static. Mathematically, the cosmological constant appears in Einstein's field equations as G mu nu plus lambda G mu nu equals 8 pi GC 14 mu nu G underscore backslash mu backslash nu plus backslash lambda G underscore backslash mu backslash nu equals backslash frac 8 backslash pi c to the power of 4 t underscore backslash mu backslash nu G mu nu plus lambda G mu nu equals c 48 pi gt mu nu. Here, G mu nu G underscore backslash mu backslash nu G mu nu, the curvature of spacetime. Lambda G mu nu backslash lambda G underscore backslash mu backslash nu lambda G mu nu, the cosmological constant, representing a uniform energy density in spacetime. T mu nu T underscore backslash mu backslash nu T mu nu, the energy momentum tensor, representing matter and energy in the universe. Einstein's lambda backslash lambda introduced a balancing term that resisted gravitational collapse, enabling a static universe. The fall of the cosmological constant. Einstein's addition seemed reasonable until the late 1920s, when Edwin Hubble's observations revealed that the universe was expanding. Hubble's discovery negated the need for a static universe and, by extension, the cosmological constant. Einstein reportedly called lambda backslash lambda his greatest blunder, discarding it as unnecessary. For decades, lambda backslash lambda was largely ignored as cosmologists embraced the idea of an expanding universe governed by the interplay of matter, energy, and gravity. The cosmological constant seemed like a relic of a bygone era, a mathematical curiosity with no physical relevance. The resurrection of lambda backslash lambda. The cosmological constant made a dramatic comeback in the late 20th century, driven by two key discoveries. 1. The accelerating universe. In the 1990s, astronomers studying distant type Ia supernovae found that the universe's expansion wasn't slowing down as expected. Instead, it was accelerating. This discovery required the presence of a repulsive force, leading scientists to resurrect lambda backslash lambda as a candidate for dark energy. 2. Cosmic microwave background (CMB) observations. Precise measurements of the CMB revealed that the universe's geometry is flat. For this to be true, the energy density of the universe needed a significant contribution from a constant energy source, consistent with lambda backslash lambda. In its modern interpretation, the cosmological constant represents the energy density of the vacuum, an inherent property of spacetime itself. The physical meaning of lambda backslash lambda. The cosmological constant can be thought of as the energy of empty space. Even in the absence of matter and radiation, quantum mechanics predicts that the vacuum is not truly empty. Instead, it is filled with fluctuating energy fields, producing a non-zero energy density. This vacuum energy exerts a repulsive pressure, causing spacetime to expand. Interestingly, the energy density of lambda backslash lambda remains constant as the universe expands. Unlike matter and radiation, which dilute over time, the vacuum energy of lambda backslash lambda does not diminish. This constancy makes it a dominant force in the universe's current and future evolution. How lambda backslash lambda drives expansion. The cosmological constant acts as a repulsive force, counteracting gravity on large scales. In the early universe, lambda backslash lambda had little influence because matter and radiation dominated the energy budget. However, as the universe expanded and matter became less dense, lambda backslash lambda grew increasingly significant. About 5 billion years ago, lambda backslash lambda overtook matter as the dominant component, accelerating the expansion of spacetime. The relationship between lambda backslash lambda and expansion can be seen in the Friedmann equations, which describe the evolution of the universe's scale factor. These equations show how lambda backslash lambda contributes to the universe's total energy density and influences its rate of growth. Observational evidence for lambda backslash lambda. Multiple lines of evidence support the existence of lambda backslash lambda. 1. Supernovae studies. The dimming of distant supernovae provides direct evidence for accelerated expansion, consistent with a cosmological constant. 2. Cosmic microwave background. The flatness of the universe observed in the CMB implies the presence of lambda backslash lambda to account for the missing energy density. 3. Galaxy clusters and large-scale structure. The distribution of galaxies and cosmic voids reflects the influence of lambda on the growth of structures over time. 4. Baryon acoustic oscillations, BAOs. Measurements of BAOs confirm the role of lambda in shaping the large-scale patterns of matter in the universe. Challenges and mysteries of lambda. Despite its success in explaining observations, the cosmological constant raises profound questions. 1. The fine-tuning problem. The observed value of lambda is incredibly small compared to theoretical predictions from quantum field theory. This discrepancy, often by a factor of 1012010^1210120, remains one of the greatest mysteries in physics. 2. The coincidence problem. Why did lambda become dominant only recently, rather than in the early or far future universe? This timing seems peculiar and has led to speculation about deeper principles governing lambda. 3. Alternative theories. Some scientists propose that lambda is not a fundamental constant, but a manifestation of evolving fields, such as quintessence or modifications to gravity itself. The role of lambda in cosmic fate. The cosmological constant plays a central role in determining the universe's ultimate destiny. If lambda remains constant, the universe will continue to expand forever, leading to a big freeze where galaxies drift apart and stars burn out. Alternatively, if lambda changes over time, it could produce different outcomes, such as a big rip, where space-time itself is torn apart, or a reversal into a big crunch. The legacy of the cosmological constant. The cosmological constant is a testament to the evolving nature of scientific understanding. What began as a mathematical fix for a static universe has become a cornerstone of modern cosmology, explaining the accelerating expansion of space-time and the dominance of dark energy. Yet lambda remains a symbol of our ignorance as much as our knowledge. It invites us to question the nature of space-time, the vacuum, and the fundamental forces shaping the cosmos. As we probe deeper into its mysteries, the cosmological constant promises to remain at the heart of our quest to understand the universe. Quantum vacuum energy. In the vast theater of the universe, even the emptiest spaces are far from truly empty. They teem with activity on quantum scales, where fleeting particles and fields fluctuate into and out of existence. This phenomenon, known as quantum vacuum energy, has profound implications for the cosmos, potentially serving as the engine behind dark energy and the expansion of space-time itself. But what exactly is quantum vacuum energy? How does it arise? And how might it connect to the accelerating expansion of the universe? Let's dive into the quantum world and explore its role in cosmic evolution. The nature of the quantum vacuum. In classical physics, a vacuum is the absence of matter, energy, and radiation, a perfect void. However, quantum mechanics reveals a more complex picture. According to the Heisenberg uncertainty principle, even in the emptiest regions of space, there is always a baseline level of energy, often called zero-point energy. This arises because particles and fields cannot remain perfectly static. Their fluctuations give rise to transient events at unimaginably small scales. These fluctuations result in the creation and annihilation of particle-antiparticle pairs, such as electrons and positrons, that appear and disappear in a dance governed by quantum laws. This foam of activity, although fleeting and seemingly insignificant, has measurable effects on the universe. Vacuum energy and the cosmological constant. Quantum vacuum energy is intrinsically tied to the concept of the cosmological constant, lambda. In general relativity, lambda is often interpreted as the energy density of the vacuum itself, providing a repulsive force that drives the expansion of spacetime. If vacuum energy is indeed the source of lambda, it would explain why the universe's expansion is accelerating. However, this connection also presents one of physics' greatest challenges. Quantum field theory predicts a vacuum energy density far larger than what is observed. Theoretical calculations suggest a value for lambda that is 1012010^1210120 times greater than what measurements of dark energy indicate. This discrepancy known as the vacuum catastrophe, remains one of the most profound mysteries in modern science. How vacuum energy arises. To understand vacuum energy, we must examine how it emerges from quantum field theory. Every point in space is governed by quantum fields, which permeate the universe. These fields fluctuate even in their lowest energy states, generating vacuum energy as a natural byproduct. 1. Zero-point energy. Zero-point energy is the lowest possible energy state of a quantum system. Even when a field is at its minimum energy, it retains a non-zero amount due to quantum fluctuations. 2. Casimir effect. The Casimir effect is a direct demonstration of vacuum energy. When two uncharged, parallel plates are placed close together in a vacuum, they experience an attractive force due to differences in vacuum energy outside and between the plates. This phenomenon highlights the tangible effects of quantum fluctuations. 3. Virtual particles. Virtual particles, which briefly appear and disappear, are another manifestation of vacuum energy. Their fleeting existence contributes to the baseline energy of the vacuum and influences interactions between particles and forces. Vacuum energy's role in cosmic expansion. Vacuum energy doesn't dilute as the universe expands. Unlike matter, which spreads out and decreases in density over time, vacuum energy remains constant per unit volume of space. This unique property makes it an ideal candidate for explaining the cosmological constant. In the early universe, vacuum energy may have played a crucial role during the period of cosmic inflation, driving the exponential expansion of spacetime. Today, it is thought to act as dark energy, dominating the universe's energy budget and accelerating its expansion. The quantum origins of inflation. The idea that vacuum energy could drive cosmic inflation stems from the behavior of quantum fields at extremely high energies. During inflation, the energy of a hypothetical scalar field, known as the inflaton, acted like vacuum energy, causing spacetime to expand at an exponential rate. As inflation ended, this energy transformed into particles and radiation, setting the stage for the Big Bang. The inflaton field is a theoretical construct, but its success in explaining inflation suggests a deep connection between quantum vacuum energy and the large-scale behavior of the universe. Challenges in understanding vacuum energy. Despite its importance, vacuum energy raises profound challenges. 1. The magnitude problem. As mentioned earlier, quantum field theory predicts a vacuum energy density vastly larger than what is observed. Reconciling this discrepancy requires new physics, potentially involving modifications to quantum mechanics, general relativity, or both. 2. The nature of zero-point energy. While zero-point energy is well understood in specific systems, its implications for cosmology remain elusive. For example, why does vacuum energy drive expansion rather than other effects? 3. Fine-tuning. The observed value of vacuum energy is incredibly small yet non-zero, suggesting precise fine-tuning. This raises questions about why the universe's energy budget aligns so perfectly to allow life and cosmic structure. Experimental evidence for vacuum energy. Although vacuum energy operates on quantum scales, its effects can be observed in several contexts. 1. Lamb shift. The Lamb shift, a tiny difference in energy levels of hydrogen atoms, arises from vacuum fluctuations interacting with the atom's electrons. 2. Casimir force. The Casimir effect, as mentioned earlier, demonstrates the physical reality of vacuum energy in laboratory conditions. 3. Dark energy observations. On cosmic scales, the accelerating expansion of the universe provides indirect evidence for vacuum energy's role as dark energy. Vacuum energy and the multiverse. One speculative idea is that vacuum energy could vary across different regions of a larger multiverse. In this scenario, our universe's vacuum energy might be fine-tuned simply because it allows for the formation of galaxies, stars, and life. This anthropic perspective is controversial, but provides a potential explanation for the otherwise puzzling value of the cosmological constant. Future research on vacuum energy. Understanding vacuum energy is a central goal of theoretical physics and cosmology. Several approaches aim to resolve its mysteries. 1. Quantum gravity. Combining quantum mechanics with general relativity could reveal how vacuum energy influences spacetime on all scales. 2. Observational advances. Missions like the James Webb Space Telescope, JWST, and the Euclid satellite will provide more precise measurements of dark energy and the universe's expansion history. 3. New theoretical models. Ideas like string theory, loop quantum gravity, and modified gravity may offer insights into the nature of vacuum energy and its connection to spacetime. The legacy of vacuum energy. Quantum vacuum energy represents a bridge between the smallest scales of quantum mechanics and the largest scales of cosmology. It is a testament to the interconnectedness of the universe, where even the empty voids are filled with dynamic processes that shape the cosmos. General relativity and gravity. The expansion of the universe is a phenomenon intimately tied to the forces and structures that govern spacetime itself. At the heart of this cosmic dance lies Einstein's theory of general relativity, which revolutionized our understanding of gravity and provided the mathematical framework for explaining the universe's dynamic behavior, including its expansion. In this chapter, we'll explore how general relativity connects gravity, spacetime, and cosmic expansion, and why it is essential for understanding the universe's past, present, and future. The Newtonian view of gravity. Before Einstein, gravity was understood through Isaac Newton's laws, which described it as a force acting between two masses. According to Newton, this force was instantaneous and universal, governing everything from falling apples to planetary orbits. While Newtonian gravity worked remarkably well for most practical purposes, it left fundamental questions unanswered. What is the nature of this force? How does gravity operate over vast cosmic distances? Why does it behave as it does? Newton's framework also struggled to explain certain phenomena, such as the orbit of Mercury, which deviated slightly from predictions. These gaps set the stage for Einstein's revolutionary insights. Einstein's general relativity. Einstein's theory of general relativity, published in 1915, replaced Newton's concept of gravity as a force with a new idea. Gravity is the curvature of spacetime. Mass and energy cause spacetime to bend, and this curvature dictates how objects move. In essence, matter tells spacetime how to curve. Spacetime tells matter how to move. This elegant framework is expressed through Einstein's field equations. G mu nu plus lambda G mu nu equals 8 pi gc 14 mu nu G underscore backslash mu backslash nu plus backslash lambda G backslash mu backslash nu equals backslash frac 8 backslash pi c to the power of 4 t underscore backslash mu backslash nu G mu nu plus lambda G mu nu equals c 48 pi gt mu nu. Here, G mu nu G underscore backslash mu backslash nu G mu nu, the curvature of spacetime. Lambda G mu nu backslash lambda G underscore backslash mu backslash nu lambda G mu nu, the cosmological constant, representing vacuum energy or dark energy. T mu nu T underscore backslash mu backslash nu T mu nu, the energy momentum tensor, which accounts for matter and energy. GGG, the gravitational constant. CCC, the speed of light. This equation encapsulates the relationship between matter, energy, and the geometry of the universe, providing a framework for understanding not only local gravitational interactions, but also the large-scale structure of the cosmos. General relativity and the expanding universe. One of the most profound implications of general relativity is that spacetime itself is dynamic. Unlike Newton's static view of the universe, Einstein's equations allow spacetime to stretch, contract, or warp in response to the energy and matter it contains. This feature led to the prediction of an expanding universe, though Einstein initially resisted the idea, introducing the cosmological constant to maintain a static model. In the 1920s, Russian physicist Alexander Friedmann and Belgian astronomer Georges Lemaitre independently applied Einstein's equations to the universe as a whole. They showed that a static universe was unstable and that the cosmos must either expand or contract. Their models, combined with Edwin Hubble's observations of receding galaxies, confirmed that the universe is indeed expanding. The role of gravity in expansion. Gravity is often thought of as a force that pulls objects together. So how does it fit into the picture of an expanding universe? The answer lies in the balance between gravitational attraction and the initial momentum from the Big Bang. 1. Early universe. In the universe's infancy, the energy density of matter and radiation was incredibly high. Gravity, driven by this density, worked to slow the expansion, creating a delicate interplay between the outward push of the Big Bang and the inward pull of gravity. 2. Transition to accelerated expansion. As the universe expanded, matter and radiation became less dense, reducing gravity's influence. This allowed dark energy, a repulsive force tied to the cosmological constant, to dominate and accelerate the expansion of spacetime. 3. Local versus cosmic effects. On smaller scales, gravity remains the dominant force. It binds stars into galaxies and galaxies into clusters, preventing these structures from being torn apart by cosmic expansion. However, on larger scales, where dark energy outweighs gravitational effects, spacetime continues to stretch. The geometry of the universe. General relativity reveals that the geometry of the universe is shaped by its total energy density. There are 3 possible configurations. Flat, Euclidean, if the energy density equals a critical value, spacetime is flat. Parallel lines remain parallel, and the universe expands forever at a steady rate. Open, hyperbolic, if the energy density is less than the critical value, spacetime is curved like a saddle. The universe expands forever, but at an accelerating rate. Closed, spherical, if the energy density exceeds the critical value, spacetime is curved like a sphere. The universe's expansion could eventually reverse, leading to a big crunch. Observations of the cosmic microwave background, CMB, show that the universe is remarkably flat, with a total energy density very close to the critical value. Gravitational waves, a cosmic symphony. One of the most remarkable predictions of general relativity is the existence of gravitational waves, ripples in spacetime caused by accelerating masses. These waves, first detected by the LIGO Observatory in 2015, provide direct evidence for the dynamic nature of spacetime. Gravitational waves not only confirm the predictions of general relativity, but also offer a new way to study the universe. They carry information about events such as black hole mergers and neutron-star collisions, revealing details about gravity in extreme conditions. The limits of general relativity. While general relativity has been incredibly successful, it is not the final word on gravity. Challenges arise when attempting to reconcile it with quantum mechanics, particularly in regions of extreme density like black holes or the early universe. The search for a unified theory of quantum gravity, such as string theory or loop quantum gravity, remains one of the greatest quests in modern physics. General relativity and cosmic fate. The ultimate fate of the universe depends on the interplay between gravity and dark energy. If dark energy remains constant, the universe will expand forever, eventually cooling to a state of entropy known as the Big Freeze. If dark energy varies over time, other scenarios like the Big Rip or Big Crunch could unfold. General relativity provides the framework for modeling these possibilities, offering insights into how spacetime will evolve over trillions of years. A dynamic universe. Einstein's theory of general relativity transformed gravity from a simple force into a profound expression of the universe's geometry. It revealed that spacetime is not static but a dynamic, evolving entity shaped by matter, energy, and dark energy. This understanding is fundamental to why the universe expands and continues to accelerate. Overcoming gravity. Gravity, the fundamental force that binds stars, planets, and galaxies together, is the glue of the cosmos. Yet, on the grandest scales, the universe expands in defiance of gravity's pull. How can this be? How does the cosmos manage to overcome the very force that governs its structures? To unravel this paradox, we must explore the delicate balance between gravitational attraction and the forces that drive the expansion of spacetime. Understanding how the universe overcomes gravity offers profound insights into its past, present, and ultimate fate. The power of gravity on cosmic scales. Gravity is unique among the fundamental forces. While electromagnetic, strong nuclear, and weak nuclear forces operate on smaller scales, gravity influences the entire universe. Its reach is limitless, and it shapes everything from planetary orbits to the clustering of galaxies. However, gravity's strength diminishes with distance, governed by the inverse square law. F equals gm1m2 or 2f equals \frac gm_1m_2 or squared F equals or 2gm1m2. Here, FFF, gravitational force, G, gravitational constant, m1, m2, m_1, m_2, m1, m2, masses of the two objects, r, distance between the objects. On smaller scales, gravity dominates, binding matter into coherent structures. But as the scale grows, other forces and phenomena begin to counteract its pull. The initial triumph of gravity. In the early universe, gravity reigned supreme. After the Big Bang, the universe was a dense, hot soup of particles, with gravity working to slow the initial outward momentum. This interplay between expansion and contraction allowed for the formation of stars, galaxies, and the intricate cosmic web. Gravity's dominance during this period was critical for creating the structures we see today. Regions of slightly higher density, seeded by quantum fluctuations during inflation, attracted more matter, growing into galaxies and clusters under the influence of gravity. However, this dominance would not last forever. The emergence of counterforces. As the universe expanded and cooled, the density of matter and radiation decreased. Gravity's strength weakened as a result, while other forces began to assert themselves. 1. Momentum of expansion. The initial energy from the Big Bang provided outward momentum, propelling spacetime to stretch. This momentum worked against gravity, slowing its effects but not stopping them entirely. 2. Dark energy. About 5 billion years ago, dark energy became the dominant force in the universe. Unlike gravity, which attracts, dark energy repels, accelerating the expansion of spacetime and overcoming gravity on cosmic scales. 3. Cosmological constant. The cosmological constant, lambda/lambda, tied to dark energy, represents a uniform energy density that drives spacetime's expansion, countering gravity's pull. The tipping point, from deceleration to acceleration. For much of the universe's history, gravity worked to decelerate the expansion. However, as the universe expanded, the density of matter decreased, while the influence of dark energy remained constant. Eventually, the balance tipped. Dark energy overtook gravity, and the expansion began to accelerate. This transition, which occurred roughly 5 billion years ago, marked a profound shift in the universe's dynamics. Galaxies that were once bound together by gravity began to drift apart at an increasing rate, as the repulsive force of dark energy overwhelmed gravity's attraction. Why gravity loses on large scales. Gravity's diminishing influence on large scales can be attributed to two key factors. 1. Dilution of matter and energy. As spacetime expands, the density of matter and energy decreases. Since gravity depends on mass and distance, this dilution weakens its effects over time. 2. Dark energy's uniformity. Dark energy does not dilute as the universe expands. Its constant energy density ensures that it grows more dominant as matter and radiation become less dense. These factors create a dynamic in which gravity's pull is increasingly overpowered by dark energy's push. Gravity's local victory. While dark energy dominates on cosmic scales, gravity remains triumphant in localized regions of the universe. Galaxies, clusters, and even superclusters are held together by gravitational forces that are much stronger than the effects of expansion. For example, the Milky Way and the Andromeda Galaxy are on a collision course due to their mutual gravitational attraction. Stars remain bound to their galaxies, unaffected by the stretching of spacetime. This distinction between local and cosmic scales explains why we don't feel the effects of expansion in our everyday lives. Gravity's dominance in these regions ensures that small-scale structures remain intact. The role of dark matter. Dark matter, an invisible form of matter that makes up about 27% of the universe, plays a crucial role in gravity's influence. Though it doesn't emit or interact with light, dark matter exerts gravitational forces, shaping the universe's structure and countering some effects of dark energy. Dark matter's presence enhances the gravitational pull within galaxies and clusters. helping to resist the expansive tendencies of dark energy on intermediate scales. Cosmic expansion versus gravitational binding. One of the most fascinating aspects of cosmic expansion is the interplay between gravitationally bound structures and unbound regions of spacetime. In regions where gravity dominates, such as galaxies and clusters, the expansion of the universe has little effect. These regions are effectively decoupled from the larger-scale dynamics of cosmic expansion. In contrast, on vast intergalactic scales, dark energy drives galaxies and galaxy clusters apart, creating ever larger voids between structures. The ultimate fate of gravity. The battle between gravity and expansion has profound implications for the universe's ultimate fate. 1. Big freeze. If dark energy continues to dominate, the universe will expand forever. Gravity will become increasingly irrelevant, with galaxies drifting apart and stars burning out, leaving a cold, dark cosmos. 2. Big rip. If dark energy's strength increases over time, it could eventually overcome gravity even within galaxies, tearing apart stars, planets, and atoms in a catastrophic big rip. 3. Big crunch. If dark energy weakens or reverses, gravity could reassert itself, halting expansion and causing the universe to collapse into a singularity. 4. Cosmic balance. If dark energy stabilizes, the universe might reach a state of equilibrium, where gravity and expansion coexist in a steady, dynamic balance. A cosmic tug-of-war. The interplay between gravity and the forces driving expansion is a cosmic tug-of-war, shaping the universe at every scale. While gravity remains a powerful architect of structure, it ultimately loses to the relentless push of dark energy on the largest scales. As we delve deeper into the universe's mysteries, we'll explore how its large-scale homogeneity and structure arise, shedding light on the forces that maintain balance and drive the evolution of cosmic expansion. Homogeneity of the universe. The universe we observe today is a marvel of complexity, with stars, galaxies, and cosmic voids forming a web-like structure that stretches across billions of light years. Yet, on the largest scales, the cosmos is remarkably uniform and isotropic, a property known as homogeneity. This large-scale evenness is a key feature of the universe and plays a critical role in its expansion. But how did the universe achieve such a homogeneous state? Why is this property crucial for understanding cosmic evolution? And what does it reveal about the forces shaping the cosmos? Let's explore the origins and implications of the universe's homogeneity. What is homogeneity? In cosmology, homogeneity refers to the idea that on sufficiently large scales, the universe is evenly distributed in terms of matter, energy, and structure. This doesn't mean that the universe is perfectly uniform. Rather, it means that the same patterns and properties appear regardless of where you look. Homogeneity is closely tied to isotropy, which states that the universe looks the same in all directions. Together, these principles form the foundation of the cosmological principle, a key assumption in modern cosmology. Evidence for homogeneity. 1. Cosmic microwave background, CMB. The CMB, the faint glow of radiation left over from the Big Bang, is one of the strongest pieces of evidence for the universe's homogeneity. Observations show that the CMB's temperature varies by less than 1 part in 100,000, indicating a remarkably uniform early universe. 2. Large-scale structure. While galaxies and clusters form intricate patterns, surveys of the universe on scales larger than a few 100 million light-years reveal a consistent distribution of matter. These patterns, such as the cosmic web, reflect the balance between gravitational collapse and expansion. 3. Hubble's law. The relationship between a galaxy's redshift and its distance, as described by Hubble's law, is consistent across the observable universe, supporting the idea that expansion occurs uniformly. The origins of homogeneity. The universe's homogeneity is thought to originate from the period of cosmic inflation, a brief but dramatic expansion that occurred in the first fraction of a second after the Big Bang. During this time, space-time expanded exponentially, smoothing out any initial irregularities. Tiny quantum fluctuations were stretched to macroscopic scales, seeding the variations that would later grow into galaxies and clusters. Inflation explains why the universe appears so uniform while still allowing for the small imperfections that give rise to structure. The role of gravity in maintaining homogeneity. While inflation established the universe's initial homogeneity, gravity plays a crucial role in maintaining and shaping it. Gravity acts as a balancing force, countering the effects of cosmic expansion by drawing matter together. This interplay creates the large-scale structures we observe while preserving the universe's overall uniformity. For example, on small scales, gravity creates dense regions like stars, galaxies, and clusters. On larger scales, the distribution of matter remains statistically uniform, reflecting the initial conditions set by inflation. The importance of homogeneity for expansion. Homogeneity is essential for understanding the universe's expansion. Without it, the cosmos would be chaotic, with regions expanding at different rates or collapsing under their own gravity. This uniformity ensures that space-time stretches consistently, preserving the large-scale structure of the universe. Mathematically, homogeneity allows for the application of the Friedmann-Lemaitre, Robertson-Walker, FLRW, metric, which describes the expansion of a homogeneous and isotropic universe. This metric forms the basis of modern cosmological models, including the Big Bang Theory. Deviations from homogeneity. While the universe is homogeneous on large scales, small-scale variations are crucial for the formation of cosmic structures. These deviations, known as anisotropies, arise from quantum fluctuations during inflation, the gravitational pull of dense regions like galaxies and clusters, interactions between dark matter, ordinary matter, and radiation. These variations are evident in the CMB as tiny temperature fluctuations, which correspond to regions of slightly higher or lower density. Over billions of years, these density variations grew under gravity to form the galaxies and clusters we see today. Homogeneity and dark energy. The universe's homogeneity also influences how dark energy drives expansion. Dark energy exerts a uniform repulsive force across space-time, accelerating expansion in all directions. This uniformity ensures that the effects of dark energy are consistent throughout the cosmos, reinforcing the large-scale evenness. However, dark energy also amplifies the separation between gravitationally bound regions, like galaxies, and unbound regions of space-time, creating vast cosmic voids that enhance the universe's web-like structure. Testing homogeneity. Astronomers continually test the universe's homogeneity through observations of distant galaxies, the CMB, and large-scale surveys. These tests aim to confirm that the cosmological principle holds true even in the most distant regions of the observable universe. If significant deviations from homogeneity were found, it could challenge current models of cosmology and suggest new physics such as large-scale anisotropies caused by unknown forces, variations in the properties of dark energy or dark matter, evidence for a multiverse or other exotic phenomena. Homogeneity and the ultimate fate of the universe. The universe's large-scale homogeneity plays a key role in determining its ultimate fate. Whether the cosmos ends in a big freeze, big rip, or big crunch depends on the balance of forces driving expansion and the uniformity of matter and energy. If homogeneity were disrupted, it could lead to unexpected scenarios such as localized collapses or uneven expansion. A universe imbalance. The homogeneity of the universe is a testament to the extraordinary balance of forces and processes that govern the cosmos. From the inflationary era to the present, this evenness has allowed for the formation of structure while preserving the consistency needed for cosmic expansion. Dark matter's indirect role. Dark matter, an invisible and enigmatic substance, makes up approximately 27% of the universe's energy-matter composition. While it doesn't emit or absorb light, its gravitational influence is undeniable, shaping galaxies, clusters, and the vast cosmic web. Though it doesn't directly drive the universe's expansion, dark matter plays a crucial indirect role by anchoring structures and influencing the evolution of space-time. But what is dark matter, and how does it impact the universe's expansion? To answer these questions, we must delve into the unseen fabric of the cosmos, exploring its gravitational fingerprints and its interplay with the forces shaping the universe. What is dark matter? Dark matter is a form of matter that interacts gravitationally but not electromagnetically. This means it doesn't emit, reflect, or absorb light, making it invisible to conventional telescopes. Despite its elusiveness, dark matter is the dominant form of matter in the universe, outweighing ordinary, baryonic, matter by a factor of about 5 to 1. Several candidates have been proposed for dark matter, including 1. Weakly interacting massive particles, WIMPs, hypothetical particles that interact only via gravity and the weak nuclear force. 2. Axions, lightweight particles predicted by certain extensions of the standard model of particle physics. 3. Sterile neutrinos, a proposed form of neutrino that doesn't interact via the weak force. 4. Primordial black holes, compact objects formed in the early universe that could mimic the effects of dark matter. While its exact nature remains a mystery, the existence of dark matter is supported by a wealth of observational evidence. Evidence for dark matter. 1. Galaxy rotation curves. The rotation speeds of stars and galaxies remain constant far from the galactic center, defying predictions based on visible matter alone. This discrepancy indicates the presence of unseen mass, dark matter, that provides the necessary gravitational pull. 2. Gravitational lensing. Dark matter bends spacetime, causing the light from distant objects to warp. Observations of galaxy clusters reveal lensing patterns that cannot be explained by visible matter alone. 3. Cosmic microwave background, CMB. The CMB's subtle temperature fluctuations reflect the influence of dark matter in the early universe, shaping the distribution of matter and energy. 4. Galaxy clusters. The total mass of galaxy clusters, inferred from gravitational effects, far exceeds the visible mass, pointing to a significant contribution from dark matter. Dark matter's role in cosmic structure. While dark matter doesn't directly influence the expansion of the universe, it plays a critical role in shaping its large-scale structure. Its gravitational pull creates the scaffolding on which galaxies and clusters form, guiding the evolution of the cosmic web. 1. Seeding structures. In the early universe, dark matter clumped together under gravity, forming dense regions that attracted ordinary matter. These regions became the seeds of galaxies, clusters, and superclusters. 2. Stabilizing galaxies. Dark matter halos surround galaxies, providing the gravitational stability needed to hold them together. Without dark matter, galaxies would not have enough mass to maintain their structure over billions of years. 3. Forming the cosmic web. The large-scale distribution of dark matter creates a web-like pattern, with dense filaments connecting massive clusters and vast voids in between. This structure is mirrored in the distribution of galaxies and reflects the initial density fluctuations from the inflationary era. The interplay between dark matter and expansion. Dark matter's role in the universe's expansion is largely indirect, mediated through its gravitational effects and its influence on structure formation. However, there are several key connections. 1. Balancing expansion and collapse. In the early universe, dark matter's gravitational pull counteracted the outward momentum of expansion, allowing matter to clump together. This balance was essential for forming stars, galaxies, and clusters. 2. Shaping void growth. On cosmic scales, dark matter influences the expansion of voids, regions of low density that grow as spacetime stretches. These voids highlight the interplay between dark matter's gravitational pull and the repulsive force of dark energy. 3. Interacting with dark energy. While dark matter and dark energy are fundamentally different, they coexist as the dominant components of the universe. Dark matter governs local structures, while dark energy drives large-scale expansion. Together, they create the dynamic balance that defines the cosmos. Dark matter and the fate of the universe. The ultimate fate of the universe depends not only on dark energy, but also on the distribution and behavior of dark matter. For example, in a universe dominated by dark energy, expansion will continue indefinitely, with dark matter structures becoming increasingly isolated. If dark energy's properties change, dark matter's gravitational influence could lead to scenarios like a big crunch or big rip, The precise role of dark matter in these outcomes remains an open question, but its gravitational effects are critical for understanding the universe's evolution. Challenges in studying dark matter. Despite its significance, dark matter remains one of the most elusive components of the universe. Key challenges include: 1. Detection. Dark matter has not yet been directly detected, despite decades of efforts using particle colliders, underground detectors, and astrophysical observations. 2. The nature problem. Identifying what dark matter is made of, whether WIMPs, axions, or something else, is a central goal of particle physics and cosmology. 3. Interactions with other forces. Dark matter's lack of electromagnetic interaction makes it difficult to study, as it leaves no direct observational signature beyond its gravitational effects. The legacy of dark matter. Dark matter is the unseen architect of the universe, shaping its structure and evolution from the earliest moments. While it doesn't directly drive expansion, its gravitational effects are essential for balancing the forces at play in the cosmos. Cosmic microwave background, CMB. The cosmic microwave background, CMB, is often described as the afterglow of the Big Bang. It is a faint, omnipresent radiation that permeates the universe, carrying a wealth of information about its earliest moments. As a relic from a time when the universe was less than 400,000 years old, the CMB is a key piece of evidence for the Big Bang theory and offers crucial insights into the universe's expansion, composition, and evolution. But what exactly is the CMB, and how does it illuminate the mysteries of cosmic expansion? Let's journey into the origins and implications of this extraordinary cosmic phenomenon. What is the CMB? The CMB is electromagnetic radiation that originated when the universe transitioned from an opaque, dense plasma to a transparent state. This moment, known as recombination, occurred approximately 380,000 years after the Big Bang. During recombination, the universe cooled to a temperature of about 3,000 Kelvin, allowing protons and electrons to combine into neutral hydrogen atoms. The free photons, no longer scattered by charged particles, traveled freely through space for the first time, creating the CMB. Today, the CMB appears as microwave radiation with a temperature of about 2.7 Kelvin, stretched to longer wavelengths by the expansion of the universe. Discovery of the CMB. The existence of the CMB was first predicted in the 1940s by physicists George Gamow, Ralph Alpher, and Robert Herman, who theorized that the remnants of the Big Bang would still be detectable as faint radiation. However, it wasn't until 1965 that the CMB was accidentally discovered by Arno Penzias and Robert Wilson, who detected an unexpected background noise while working with a radio antenna. This discovery provided direct evidence for the Big Bang theory and earned them the Nobel Prize in Physics. The properties of the CMB. The CMB is remarkable for its uniformity. It is almost perfectly isotropic, with tiny variations in temperature of only a few parts per million. These variations, or anisotropies, reflect the seeds of the large-scale structure of the universe, encoding information about its early density fluctuations. Key properties of the CMB include: 1. Temperature. The CMB's average temperature is 2.725 Kelvin, corresponding to microwave wavelengths. 2. Spectrum. The CMB exhibits a nearly perfect blackbody spectrum, confirming its origin as thermal radiation from the early universe. 3. Anisotropies. Small temperature fluctuations in the CMB reveal differences in density and composition that later grew into galaxies, clusters, and cosmic voids. The CMB and expansion. The CMB is a powerful tool for understanding the expansion of the universe. As the universe expands, the wavelengths of CMB photons stretch, lowering their energy and shifting them to the microwave part of the spectrum. This process, known as cosmological redshift, provides a direct measure of how much the universe has expanded since the CMB was emitted. By analyzing the CMB, scientists can determine the universe's age, approximately 13.8 billion years, the rate of expansion, encoded in the anisotropies and linked to the Hubble constant, the geometry of the universe. The CMB reveals that spacetime is flat on large scales, consistent with an expanding universe dominated by dark energy. The structure of the CMB. Detailed observations of the CMB have revealed a rich tapestry of information encoded in its anisotropies. These small fluctuations are the result of quantum fluctuations during inflation, magnified to macroscopic scales. They provide a snapshot of the universe's density and energy distribution at a critical moment in its history. The CMB's anisotropies can be analyzed through power spectra, which describe the distribution of temperature fluctuations across different angular scales. Key features include: the first peak indicates the largest scale of density fluctuations, corresponding to the size of the sound horizon at recombination. Subsequent peaks reflect oscillations in the plasma of the early universe, shaped by interactions between dark matter, ordinary matter, and radiation. Observational milestones. Advances in technology have allowed increasingly precise measurements of the CMB, revealing ever more details about the universe's history and composition. Key missions include: 1. COBE, Cosmic Background Explorer. Launched in 1989, COBE confirmed the CMB's blackbody spectrum and detected its anisotropies for the first time. 2. WMAP, Wilkinson Microwave Anisotropy Probe. From 2001 to 2010, WMAP mapped the CMB with higher precision, providing detailed measurements of the universe's age, composition, and geometry. 3. Planck Satellite. The Planck mission, launched in 2009, achieved the most detailed observations of the CMB to date, refining estimates of the Hubble constant and dark energy's influence. The CMB and the universe's composition. The CMB anisotropies encode information about the relative contributions of matter, radiation, and dark energy to the universe's total energy density. These measurements reveal that ordinary matter makes up about 5% of the universe. Dark matter accounts for 27%. Dark energy dominates at 68%. This composition determines the universe's expansion history and ultimate fate. Challenges and mysteries. While the CMB provides a wealth of information, it also raises new questions. 1. The horizon problem. The CMB's uniformity across vast distances suggests that regions of the early universe were in causal contact. Yet this seems impossible under standard Big Bang models. Inflation solves this problem by positing a rapid early expansion. 2. The Hubble tension. Measurements of the Hubble constant from the CMB differ slightly from those based on nearby galaxies and supernovae, raising questions about the nature of dark energy and the expansion rate. 3. Isotropy deviations. Some studies suggest slight deviations from perfect isotropy, which could hint at new physics or the influence of the multiverse. The legacy of the CMB. The cosmic microwave background is a cosmic time capsule, preserving a snapshot of the universe at a critical moment in its infancy. Its discovery and ongoing study have transformed our understanding of the cosmos, confirming the Big Bang, revealing the universe's composition, and illuminating the forces driving expansion. Measuring expansion rates. The universe is expanding, a fact established by decades of astronomical observation and theoretical development. But how do we measure the rate of this expansion? Understanding how space-time stretches requires precise methods and instruments capable of probing both the nearby and distant cosmos. This chapter explores the tools, techniques, and challenges involved in measuring the universe's expansion rates, focusing on the famous Hubble constant, H0, H_0, H0, and its role in revealing the dynamic nature of the cosmos. The Hubble constant. The Hubble constant, H0, H_0, H0, represents the rate of the universe's expansion, expressed as the speed at which galaxies recede per unit of distance. Its value is typically given in units of kilometers per second per megaparsec, km/s/mpc, where a megaparsec equals approximately 3.26 million light-years. Mathematically, the relationship is expressed as V equals H0 dV equals H_0 backslash that dV equals H0d. Here, VVV, the recessional velocity of a galaxy, H0, H_0, H0, the Hubble constant, DDD, the galaxy's distance from Earth. This equation forms the basis for understanding cosmic expansion, allowing astronomers to calculate the rate at which space-time is stretching. Methods for measuring expansion rates. 1. Standard candles. Standard candles are astronomical objects with known intrinsic luminosity. By comparing their observed brightness to their intrinsic luminosity, astronomers can calculate their distance. Type Ia supernovae. These stellar explosions are consistent in brightness and serve as reliable standard candles for measuring distances to faraway galaxies. Cepheid variables. Pulsating stars with predictable luminosity variations, often used to measure distances to nearby galaxies. 2. Redshift. The redshift of light from distant galaxies provides a measure of their recessional velocity due to the stretching of spacetime. Combining redshift data with distance measurements yields the Hubble constant. 3. Cosmic microwave background, CMB. Observations of the CMB provide an indirect measure of H0, H_0, by analyzing the universe's geometry and expansion history. This method involves fitting cosmological models to the CMB's anisotropies. 4. Baryon acoustic oscillations, BAOs. BAOs are ripples in the distribution of galaxies caused by sound waves in the early universe. These ripples serve as a standard ruler for measuring distances and expansion rates. 5. Gravitational lensing. The bending of light by massive objects provides additional constraints on cosmic expansion. By studying lensing patterns, astronomers can infer the Hubble constant and the universe's overall geometry. The Hubble tension. Despite the precision of modern measurements, a significant discrepancy exists between values of H0, H_0 obtained through different methods. Local measurements. Using standard candles like Cepheid variables and Type Ia supernovae yields a higher value for H0, H_0, around 73 kilometers per second per MPC. CMB measurements. Observations of the CMB, combined with cosmological models, suggest a lower value, around 67 kilometers per second per MPC. This disagreement, known as the Hubble tension, raises questions about whether the discrepancy is due to systematic errors in measurements or hints at new physics, such as evolving dark energy or interactions between dark matter and radiation. Challenges in measuring expansion rates. 1. Distance uncertainties. Measuring cosmic distances is inherently challenging. Standard candles, while reliable, can be affected by factors like dust extinction and variations in intrinsic luminosity. 2. Redshift interpretation. Redshift is influenced by both the universe's expansion and local gravitational effects, requiring careful analysis to disentangle these contributions. 3. Cosmological model dependence. Methods like CMB and BAO analyses depend on underlying cosmological models. If these models are incomplete or inaccurate, the inferred value of H0, H_0 may be biased. Recent advances and future prospects. 1. Improved instruments. Modern telescopes, such as the Hubble Space Telescope and the James Webb Space Telescope, provide unprecedented precision in measuring distances and redshifts. 2. Standard sirens. Gravitational wave events, such as neutron star mergers, offer a new way to measure distances. These standard sirens are independent of electromagnetic observations and could help resolve the Hubble tension. 3. Next-generation surveys. Missions like Euclid and the Vera C. Rubin Observatory aim to map the universe in greater detail, refining measurements of H0, H_0, and probing the nature of dark energy. The importance of measuring expansion rates. Understanding the rate of the universe's expansion is critical for answering fundamental questions about its origin, composition, and fate. The value of H0, H_0 influences estimates of the universe's age, the nature of dark energy, and predictions about the cosmos's ultimate destiny. The ongoing effort to measure H0, H_0 represents a collaboration between observational astronomy, theoretical physics, and advanced technology. Each new observation brings us closer to resolving the mysteries of cosmic expansion, a window into the universe's evolution. The Hubble constant serves as a bridge between the universe's past and its future. By studying the expansion rate, astronomers can trace the cosmos's history back to the Big Bang and project its evolution billions of years into the future. Accelerated expansion. For much of the 20th century, astronomers assumed that the universe's expansion, set in motion by the Big Bang, was gradually slowing down under the pull of gravity. However, in the late 1990s, a groundbreaking discovery overturned this assumption. The universe's expansion is not slowing, it is accelerating. This revelation, one of the most significant in modern cosmology, pointed to the existence of a mysterious force, now known as dark energy. But what drives this accelerated expansion? What does it mean for the future of the cosmos? And how do we study this elusive phenomenon? In this chapter, we'll explore the forces behind accelerated expansion and its profound implications. The discovery of accelerated expansion. The discovery of the universe's accelerated expansion came from studies of type Ia supernovae, which serve as standard candles for measuring cosmic distances. In 1998, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed that distant supernovae were dimmer, and therefore farther away, than expected under a slowing expansion. These observations revealed that the universe's expansion rate was increasing, contrary to predictions based on the gravitational influence of matter. This unexpected acceleration required a new explanation, a repulsive force or energy that counteracted gravity on cosmic scales. The role of dark energy. Dark energy is the name given to the mysterious force driving accelerated expansion. It accounts for roughly 68% of the universe's total energy density, dwarfing the contributions of ordinary matter, 5%, and dark matter, 27%. Dark energy's defining characteristic is its negative pressure, which causes space-time to stretch. Unlike matter and radiation, which dilute as the universe expands, dark energy's density remains constant, or nearly so, allowing it to dominate the universe's dynamics as matter and radiation become less dense over time. Evidence for accelerated expansion. 1. Type Ia supernovae. Observations of distant supernovae provide direct evidence for accelerated expansion. Their unexpected dimness indicates that spacetime has stretched more than would be expected under a decelerating model. 2. Cosmic microwave background, CMB. The CMB's anisotropies reveal the geometry of the universe and the influence of dark energy. Observations show that the universe is flat, requiring the presence of dark energy to account for its energy density. 3. Baryon acoustic oscillations, BAOs. BAOs, ripples in the distribution of galaxies, serve as a cosmic ruler for measuring distances. These measurements confirm the accelerated expansion over billions of years. 4. Large-scale structure. The distribution and growth of galaxies and clusters reflect the interplay between gravity and dark energy. Accelerated expansion suppresses the formation of large structures, consistent with observations. How accelerated expansion works. The dynamics of accelerated expansion are governed by the Friedmann equations, which describe how the universe's scale factor evolves over time. The key term in these equations is the cosmological constant, lambda/lambda, which represents dark energy's contribution to the universe's energy density. Mathematically, AA equals minus 4 pi g3, rho plus 3p, \frac \a equals dash \frac 4 pi g3, \rho plus 3p, a equals minus 34 pi g, rho plus 3p. Here, AAA, the scale factor describing the size of the universe. Rho, energy density. PPP, pressure. For ordinary matter and radiation, PPP is positive, leading to deceleration. However, for dark energy, PPP is negative, resulting in acceleration. The nature of dark energy. Dark energy's precise nature remains one of the greatest mysteries in science. Several theories attempt to explain it. 1. Cosmological constant, lambda/lambda. The simplest explanation is that dark energy is a constant energy density inherent to spacetime. This interpretation aligns with Einstein's cosmological constant, reintroduced to explain accelerated expansion. 2. Quintessence. Dark energy could be a dynamic field that evolves over time. Unlike the cosmological constant, quintessence varies in strength and influence, potentially leading to different cosmic fates. 3. Modified gravity. Some theories propose that dark energy arises from modifications to general relativity, altering how gravity behaves on large scales. 4. Emergent phenomena. Dark energy might be an emergent property of quantum fields, entropy, or other fundamental processes not yet fully understood. The impact of accelerated expansion. Accelerated expansion has profound effects on the universe's structure and evolution. 1. Cosmic voids. Accelerated expansion stretches spacetime, enlarging the voids between galaxies and creating a more fragmented cosmic web. 2. Galaxy isolation. Over time, accelerated expansion will isolate galaxies as they recede beyond the observable universe. Eventually, only the nearest galaxies, gravitationally bound to us, will remain visible. 3. Suppression of structure formation. Dark energy's repulsive force counteracts gravity, slowing the growth of galaxies and clusters. This effect is already observable in the universe's large-scale structure. Observational challenges. Studying accelerated expansion is challenging due to its vast scale and subtle effects. Key challenges include precision in measuring H0, H_0, H0, the Hubble tension, discrepancies between local and early universe measurements of the Hubble constant, complicates interpretations of accelerated expansion. Distinguishing dark energy models. Observations must distinguish between a true cosmological constant and dynamic models like quintessence. Interplay with dark matter. Understanding how dark energy interacts with dark matter is critical for refining cosmological models. The future of accelerated expansion. The universe's accelerated expansion suggests several possible fates. 1. Big freeze. If dark energy remains constant, galaxies will drift apart, stars will burn out, and the universe will cool into a dark, lifeless state. 2. Big rip. If dark energy strengthens over time, it could eventually tear apart galaxies, stars, and even atoms, culminating in a catastrophic big rip. 3. Cosmic rebound. If dark energy weakens or reverses, the universe could stop expanding and contract into a big crunch. 4. Stable expansion. If dark energy stabilizes, the universe may reach a steady state, with expansion continuing indefinitely at a constant rate. Accelerated expansion and the fate of the cosmos. The discovery of accelerated expansion has reshaped our understanding of the universe, highlighting the dominance of dark energy and raising profound questions about the nature of spacetime. While we've made tremendous progress in understanding this phenomenon, many mysteries remain. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.